Please join me in welcoming to the stage Aaron Sant-Miller, Director of Data Science and AI ML at Booz Allen Hamilton, who are presenting their AI-enabled cyber threat detection platform.
Thanks, Sam. Hey, you guys hear me all right? Okay, awesome. So I've got, got to switch the displays here. Yeah. All right, there we go. Okay, so I'm going to talk a little bit about why cyber AI is really, really hard. I think how we've taken an approach to make it a little bit more tractable and appropriate, and then highlight how we've integrated cyber and AI into operations. So to start, okay, this is my slide that, as somebody who's worked in AI and cyber for a long time, this is my slide that tells you my entire job might be a sham. So these are the challenges to doing AI and cyber, and why I would say, in a lot of ways, AI and cyber has overwhelmingly struggled to integrate effectively and make an impact in operations. There's challenges, I would say, in three core pillars. The first is expectations. So a lot of organizations, when they want to add AI to defensive cyber operations, they're thinking about adding the wrong thing or having the wrong type of impact. So in a lot of cases, they think, oh, it's going to help me with automation. It's going to speed up how I do things. It's going to reduce the number of people I have operating in my security operations center. And that's not always the case. And if you want to improve automation and efficiency, there's often more effective ways to do that, and a lot of tools in the cyber domain that help you with that already. Secondarily, a lot of folks think they're going to build a model and it's just going to find bad guys. So it's going to differentiate good from bad very, very clearly. And in live operations, you're going to see, here are all the bad guys and here are all the good guys. And that's not really how it works. That's not how cyber operations work. And AI isn't going to do that for you just at the turn of a hat. Secondarily, there's a lot of different challenges that come into play for actually integrating models and integrating software for AI and cyber. First, data for cyber is just very, very fast moving, which adds a couple different constraints. One, it's very fast, and there's challenges with that from a compute perspective. And two, I would say it introduces other challenges for model effectiveness and efficiency. So you're processing 50,000 events per second. If your false positive rate on a model is 1%, that's a lot of false positives per second that you're sending to analysts. Also, I would say the way that you integrate models into operational platforms is important. Cyber operators are really busy. They're already overwhelmed. If you're not giving them outputs in an efficient and effective way that makes their life easier, they get alienated pretty quickly. Also, use cases. So cyber operators, again, don't think about this is a bad event, this is a good event. They think about a cyber kill chain. So what they want is they want models that help them identify specific behaviors in the kill chain to more effectively conduct their operations, not just say this was a bad thing, move on, because that's not how they think. That's not how cyber operations happen. And then most importantly, we have data challenges. There is not any subset or standard for reusable labeled data assets. A lot of the open source available labeled data, the benchmarking data, is very old on networks that aren't representative of how networks operate today. And then secondarily, unsupervised approaches often struggle. That's partially because cyber behavior is inherently anomalous. Like if we take my day, for example, most days I start work at 8:30, 9 o'clock. Today, I didn't open my computer. I came to this conference. Someone might flag me as, hey, he's connected to a network he doesn't usually connect with. Something bad has happened. No, this is just part of my day-to-day job. So traditional anomaly detection doesn't work the same way it does in other domains. So I'm going to step through, I think, two ways that we're tackling this problem. So the first is architecturally, and then the second is methodologically. So architecturally, the key piece here is that that's not going to show up well, that we're deploying all of our AI and analytic models in this streaming analytic pipeline. Now, there's a few reasons we do that. Most importantly, it's that, one, we can keep pace with the rate that data moves through the pipeline so that we can alert in real time and provide detections in real time. And secondarily, it makes it very easy for us to add data directly into existing platforms. So as I mentioned before, cyber operators, they like to conduct their operations through the SIM, your Splunks and Elasticsearch. They want the outputs of models directly in those tools where it's easy to add to their existing workflows and operations. So we want to implement an architecture for AI deployment that works with this. This is very much the standardized pub/sub architecture, which also lets you add new models into the ecosystem and new models into the process without introducing additional barriers or constraints and disrupting existing data flows and pipelines. Okay, methodologically, I go back to my point around the cyber kill chain. This has been really effective for us, which is instead of building a model to say, hey, this is a bad event, this is a good event, this is a bad log, this is a good log, let's think the way that a cyber operator does and let them tell us where models should fit within the ecosystem. So cyber hunters, when they go through an investigation or they look for malicious traffic, they'll break everything down into a specific kill chain. Then they'll operate and segment their actions through that kill chain to detect a malicious adversary with a stepwise process in the way that an adversary would exploit or attack a network. What we've done is we implement AI in a similar approach. So this is one example on how we've decomposed a kill chain, and then I'll actually walk through a specific example that we're implementing today. But first, what we'll do is we'll look to detect a specific TTP. This is like a common adversary technique, tactic, and protocol that they'll use to exploit or attack a network. Second, what we'll do is we'll correlate that with context. That's often what cyber operators do. They'll say, hey, something bad happened. I recognize the specific type of attack that I've seen on networks that adversaries often use, that a specific APT might be often using. I want to correlate that with context. I want to understand a little bit more about what threat data is out there, what some of my researchers have found about this particular APT or this particular behavior, or some of the specific indicators that the model is flagging. Then what you want to do is you want to look for a behavior shift. So oftentimes an adversary will try to do something, but not actually create a compromise. So they'll attack your network, but you have controls in place, configurations in place that prevent something bad from actually happening. So what we want to do is we want to say, hey, adversary tried something and they actually did something effectively because the behaviors on your devices, on your network have substantively changed in a way that is notable and potentially indicating something of interest. Oftentimes that's data exfiltration or a new behavior that could be indicative of something lateral movement that an adversary is doing on your network. And then finally, what you want to do is you want to curate all of that to an analyst or a user in one way that they can see all that information together so they can investigate their own way. What we've found is that the analysts and the users, they want all of that information put together in one dashboard so they can quickly find what they need to see, find all that context, find what the model's detected, but let them continue to investigate with the tools that they're familiar with and they're comfortable with. The key piece that I'll add here is that to the end user, it doesn't really matter that it's AI. They have a lot of techniques that they use to detect adversary behaviors. A model is just another tool in that toolkit. It's just another piece of information that's presented to them in their end dashboard and end analyst interface. Okay. So what I've done is I've taken that same flow and all right, I don't have the slide didn't pull over. I'll walk through an example here with each of these phases. So the first, the detect the TTP. One of the attacks that we often see adversaries using is something called typo squatting, which is where someone takes a domain that you trust or a URL that you would obviously think is benign, but they change it in a way that a small typo or a small structural change in it might look malicious. So the example I always use is Google. If I replaced the L with a 1, visually it would look very similar, but the string itself is functionally different. So what adversaries will do is they'll create domains like that look benign but are actually malicious. This is something that they'll often use in phishing attempts or spear phishing attempts. So this is a common technique that adversaries will use. So we've built AI and machine learning models that are very good at finding that. We use a series of methods that actually look at the visual similarity of a domain with the structural similarity of the domain compared to a whitelist and look for something called a homograph. So we're very good at finding that particular TTP. But just because a domain looks like a trusted TTP doesn't mean that domain is bad or that an adversary is trying to do something malicious on your network. So we want to add more information. So what we'll do is we'll correlate that with additional context. There are a lot of threat sources out there that can be really valuable. We use something called VirusTotal. It's a threat source that a lot of folks use in cyber operations that can give you context about domains and IPs and information on that. So we'll correlate that in. Hey, has someone seen this domain? Is it associated with the threat actor? Or we'll pull in domain registry data. Hey, was this domain just registered in the last 12 hours? Is it been registered for a while? Is it trusted or multiple people using it? Getting some of that context all in. Note, this is all happening in that architecture that I showed previously on the data stream. So the data comes in, the model runs on it, it adds the enrichment, we add the context as well. So all of this is getting correlated in rows. So in this case, you have the domain, you have, is it likely to be typo squatting or this particular TTP? And then here's all the context that we were able to pull out that correlates with that domain. And then finally, we'll go to the device that accessed this domain or went to this or the user's account, and we'll say, hey, did any behaviors notably shift for them? Was there a notable transfer of data, an anomalously large packet exchange to an external IP, an hour or two after they access the domain? Or are there certain movements or access attempts that account is trying to make that they don't typically make? So you have a series of models that are traditional kind of unsupervised anomaly detection models looking for behavior shifts, but they're only flagging after you've seen a potential intrusion to a given user or a given analyst. All of this then gets curated and published into the analyst dashboard. So the end user, the end cyber analyst, gets all this within their interface, within their tool, within their platform, where they can then execute this investigation through this kill train for a specific TTP and a specific attack type that they're familiar with. So I have a couple slides here and screenshots that one will show really simply how this appears in an analyst interface. And then one talks a little bit more about how we're thinking about this from a machine learning perspective that I want to dig into a little bit more. Oh, there's the slide. Okay. Okay, so this is what it looks like at the end of the day for an analyst. I'm just going to stop here for a second. This is Elasticsearch, Kibana. Everyone's probably familiar with this. The key piece here, though, is that what we're doing is we're presenting this to them in their own interface and in their own tool. And then they have outputs like this that will flag specific events that are of interest with an AI score that they can filter off of. Key piece here is that this output is landing in their tool that they use every day. It's easy for them to access, and they're able to pivot off this and query from this to all the other context and data that they're interested in. This is a piece I want to talk about very much so, more on how these models then are monitored as they're detecting these attacks and pursuing the detection of adversaries. So as I mentioned before, there isn't a good set of representative, good training data for AI models. So what we want to do is train models, deploy them onto networks, and then make sure as they're running inference that they're making those inferences robustly, effectively, and appropriately. So what we want to do is we want to monitor those models in real time for things like epistemic uncertainty, which is uncertainty in the model's inferences that it's making on real data that it's seeing that might not be representative of the data that it was trained off of, or things like drift either in the model's input space or the output space. So as I mentioned, those models are all running on that streaming data. They're processing that log data. They're looking for specific behaviors. We're also monitoring the models themselves. So what we're looking at for those models is, hey, are we seeing notable shifts in the model input space? Are we seeing notable shifts in the model output space that don't correlate with events of interest? Or is the model flagging high degrees of uncertainty? So we have tools like this. This is just a representation in Grafana, which is an open source tool, very useful for real-time monitoring, real-time dashboarding. We're using Prometheus on the back end to scrape metrics and present them to Grafana. The key piece here is what we've done is we built a tool that helps us analyze data drift in the input space. So what we're tracking here and what I've circled here are two actual occurrences when there is drift in the input space. So that could mean one of two things. One, it could mean something changed on the network that is notable and of interest, or it could mean that the input space is changing in a way that might impact the model's inferences, that those model inferences are no longer appropriate or robust because the data that it's seeing in real time is not representative of the data that it was trained off of, which is a key piece that we want to present to analysts. The last thing I'll mention on this slide is that all of these outputs are then published into the end user, the end dashboard, the same way the model outputs are. So you don't just get a model that says, hey, I think typo squatting occurred on this network. We'll say, hey, we think typo squatting occurred on this network, and here's our confidence in the model's inference and its confidence in making that assessment. Again, that's really important. I've got like a minute left here. I kind of want to close the loop on that. Several years ago at RSA, I think there was a study that showed 70% of presentations talked about AI in cyber. The next year, that dropped down to 25%. Now, the key piece there was that everyone pushed forward on AI and machine learning, and it didn't go particularly well. That alienated a lot of analysts and users who were already really busy and already struggling to keep up with threats that are evolving every day. And so it's really important that when we fold AI into operations, when we present these outputs to users, that they're conveyed in a way that's very transparent, and that's conveyed in a way that integrates with their operations with the way that they want to. We had a lot of struggles early on folding AI into a lot of live operations, but we've had more success of late as we've had more investment from the analysts. So that back and forth between your cyber operators and your data scientists is critically important because, again, I think we, to some degree, failed at the way that we added this into operation several years ago, and now we're working to rebuild a lot of that trust. That is what I have for the presentation. I don't know how much time I have. My clock is telling me I don't have much. But if folks have, oh, I think I'm getting the pinwheels. I think that means it's time for me to go. But thank you, everybody. I'll be hanging around afterwards if folks have questions. Happy to talk through for any like finer detail in the technical implementation, the models, the methods, all that. But again, I think the key piece here is it's the approach and the methods that you apply that are really important, and not thinking that there's going to be a silver bullet to throwing AI at cyber, because there's a lot of differences in the way that cyber operates from a lot of other traditional domains of AI application. So thank you.